Welcome to The Explainer. Today we're digging into a fundamental concept from physics and math that explains why some journeys are, well, perfectly normal and repeatable, and others, like the kind you see in art, are just flat out impossible.
Okay, so here's how we're going to tackle this. We'll start with an idea that you can probably feel in your gut. Then we'll build up the mathematical language we need to describe it. We'll see how that language defines a special class of fields, uncover its deep connection to the conservation of energy, and then, right at the end, we'll hit a really fascinating twist.
So, to really get our heads around this, let's just forget about the heavy equations for a minute and start with a simple question about a journey.
Have you ever seen this famous M.C. Escher print, Ascending and Descending? It perfectly captures this paradox. You've got these monks on a staircase, and they are perpetually climbing, but they never actually get any higher. They're just walking in a closed loop, always going up, but somehow ending up right back where they began. In our world, a fundamental force makes this kind of thing impossible.
Yeah, in the real world, this is a total no-go, and it's all because the force of gravity creates what we call a conservative field. Now, what does that really mean? It just means that the total work done by gravity when you return to your starting point is always, and I mean always, zero. You have to go down exactly as much as you went up. There's no cheating the system.
So here's the crucial point. For gravity, the path you take just doesn't matter. All that matters is your start and end point. You could take a long, winding, scenic route up a mountain, or you could climb straight up the sheer cliff face. It makes no difference. The gain in your gravitational potential energy is exactly the same. And this is the core idea we're talking about: path independence.
Okay, so to describe this invisible landscape of forces in the language of math, we need to build ourselves a special toolkit. First thing we need is the concept of a vector field. Just picture a weather map that shows the wind. At every single point on that map, there's a little arrow telling you not just the speed of the wind, but also the direction it's blowing. That's a vector field. Simple as that.
All right, our first tool is something called the gradient. So if a vector field is like that wind map, a scalar field is more like a temperature map. It just gives you a number, a temperature, at every point. What the gradient does is it takes that temperature map and creates a vector at every point that tells you the direction of the fastest temperature increase. It tells you which way is uphill.
And this visual really makes it click, right? Those ovals are basically contour lines, just like on a topographical map, where a value, say altitude, is constant. Now notice how the gradient vectors, those little arrows, always point straight uphill. They're always pointing in the direction of the steepest climb, exactly perpendicular to those contour lines. Okay, tool number 2 for our toolkit is divergence. This one's a little different. It tells us if a field is flowing outward from a point, what we call a source, or if it's flowing inward, which we'd call a sink. And the best way to think about it is with faucets and drains. If the divergence at a certain spot is positive, it's like a faucet is on. More stuff is flowing out than flowing in. If it's negative, it's a drain, sucking things in. And if the divergence is 0, well, that means the amount of fluid flowing into any tiny volume is exactly the same as the amount flowing out. It's perfectly balanced.
And that brings us to our final tool, curl. And yeah, as the name kind of suggests, it measures how much a field swirls or rotates right around a specific point.
This is the perfect analogy. Imagine you could shrink down and drop a tiny little paddle wheel into a river. Even if the river as a whole is flowing in a perfectly straight line, there might be little eddies, little local rotations in the water that would make that paddle wheel start to spin. That's exactly what curl is designed to detect.
Okay, so now we've got our toolkit: gradient, divergence, and curl. With these, we can get super precise and finally define what makes a vector field conservative.
So it turns out these 3 different properties you see here, they're all just equivalent ways of saying the exact same thing. A field is conservative if the work done is path independent. That was our mountain climbing example. That's the same as saying the field is the gradient of some scalar potential function, our altitude map. And that in turn is the exact same thing as saying the field has 0 curl everywhere, no tiny spinning paddle wheels. It's pretty amazing. If a field has one of these properties, it has all 3. So you might be thinking, okay, cool math, but so what? Well, this is where it gets really important. This whole mathematical idea is the absolute foundation of one of the most important laws in all of physics. And this isn't just some abstract thing on a blackboard. We're talking about the fundamental forces that run the universe. 2 of the big ones, gravity and the electrostatic force, are described by these conservative vector fields. And that has some massive real-world physical consequences.
And because these forces are conservative, we get to define these incredibly useful concepts like potential energy and voltage. Think about it. These quantities only depend on an object's position, not on the crazy, winding path it took to get there. And that's all thanks to path independence.
And here it is, the big payoff. The mathematical property of a force field being conservative is the very reason energy is conserved in these systems. Any loss in potential energy is perfectly converted into kinetic energy, and vice versa. The books always balance. Nothing is ever lost.
But like with any good set of rules, there's a loophole, a really fascinating exception where a field can look and act conservative, but actually isn't. Okay, so remember how we said if the curl is 0, the field is conservative? Well, I kind of left out one tiny but crucial detail. It turns out the shape of the space where the field exists matters a lot. Specifically, the space can't have any holes running through it.
This right here is the fine print. If you have a region with a hole in it, and I mean literally, like if you took 3D space and just plucked out the entire z-axis, everything changes. You can actually create a vector field that has 0 curl everywhere, but is still not conservative. This creates a bizarre loophole where you could travel in a loop around that hole and come back having done net work. All of a sudden, that impossible journey of Escher's monks becomes, at least theoretically, possible.
And this deep connection, this link between a local property, like curl, and the global shape or topology of space, is such a powerful idea in both math and physics. It really makes you wonder, doesn't it? What other secrets of the universe are hidden not just in the equations themselves, but in the very geometry of the space they describe?